All right, so we're going to practice drawing some more Lewis dot structures. All right, let's draw a Lewis dot structure for carbon dioxide, CO2. This is a very classic Lewis dot structure to draw, which teaches us about double bonds. Double bonds. Okay, so can you help me out, Fred?
I'm ready.
Okay, here we go. CO2. What's the first thing we need to do?
I can't remember.
Okay, very good. We need to identify the central atom.
Oh yeah, central atom, that's carbon.
Very good. Carbon always wants to be the central atom, and in this case there's only one carbon, so that's how we would know that the central atom is carbon. All right, then what?
You draw your oxygens?
That's right. We bind whatever's left with a bond to the central atom. Okay, then what?
We need to know how many valence electrons, right?
That's right. You need to know how many valence electrons there are, so we add it up. How many carbon, or how many did carbon bring?
Is it in the fourth row?
That's right. Fourth column, not row, right, of the periodic table. 1, 2, 3, 4. So it brings 4. While we're here, let's see what oxygen.
Oh, it's 6.
That's right. So carbon brings 4. Each oxygen brings 6. That's what?
14?
6 plus 4.
16?
Yeah, that's right. So we have 16 valence electrons. 6 times 2, 12 plus the 4. All right? So 16 valence electrons. Now, how many valence electrons do we already have up there?
What do you mean?
Well, we've drawn our our skeleton structure, and we've already used up 4 valence electrons. Is that right?
Oh yeah, so we only have 12 left.
Okay, very good. So I have to subtract 4 valence electrons for my skeleton structure bonds that are already there, leaving me with 12 valence electrons. So what's next?
Let's put electrons on carbon so it has an octet.
Very good. I'll put in 4 there because I saw that it had available to it only 1, 2, 3, 4. But now, how many electrons does it have available to it?
It has, let's see, available to it, do you count bonds as 2?
Yeah, that's right. You count bonds as 2.
So it has 8 electrons available to it.
Very good. 1, 2, 3, 4, 5, 6, 7, 8. That's the carbon. How many electrons does that oxygen have available to it?
The bond count says 2, right?
That's right. So that's 2 bonds, 2 electrons there. So oxygen only has 2 electrons available to it. So what do we got to do?
Give it 6.
All right. So if I give it 6, 1, 2, 3, 4, 5, 6, minus 6 valence electrons, right? So what's its, how many electrons are available to that oxygen now?
8.
Very good. And how many electrons over here?
You need 6 there too.
All right. Now we come into a problem. I only have 2 valence electrons left. 1, 2. And I'm out of electrons.
Why did we only had 16 to start?
That's right. You count how many electrons are brought by the different atoms, right? And that's what governs how many electrons you start off with.
Okay, so what do we do now?
Well, now is where we can introduce what we call double bonds. Double bonds. And bringing in double bonds will allow more electron density to be shared, because that's what needs to happen here. There's not enough for everybody to have 8 the way we've drawn it. So we don't have the correct Lewis dot structure yet. But if I take these electrons, for example, and I use an arrow and show that I'm pushing the electrons out into the bond, then my new structure will look like this. And we can recalculate and see if that improved things.
Yeah, okay, so now oxygen has more electrons on the oxygen on the left has more electrons available to it.
That's right. It has how many now?
Do you count both those bonds as 2?
That's right. 1, 2, 3, 4, 5, 6. So it has 6 electrons available to it. So this oxygen still has the 8. How about this carbon? Did it lose electrons?
I think so.
So count it up. How much electron density does it have available to it?
1, 2, 3, 4, 5, 6, 7, 8. It still has 8, so it didn't lose any because those 2 are just being shared now.
That's right. So those 2 went into sharing, so it still has those available to it. But we're still not done, are we?
No, because we need the electrons, we need more on the oxygen on the left.
That's right. So what if I bring these electrons in and form a triple bond?
You can do that?
Sure, you can do that. Carbon, triple bond here, oxygen, right? Now, does everybody have 8 electrons available to it?
Yeah, everybody has 8 electrons available to it.
Okay, good. Now, do you remember what we're supposed to do after we reach this point to verify that the Lewis dot structure is correct?
Something about making sure that the number of electrons that it has right around it was equal to something.
That's right, good. We look at how many electrons are not just available to the atom, but right around the atom. So how many electrons are available to this atom?
That was 8.
But how many are right around it?
I can't remember. How do you do that?
You count 1, 2, 3, 4, 5, 6, and this just counts as 1 electron right around the oxygen. So that's 7 electrons right around it. Okay? And then we calculate what are called formal charges. Formal charges are the number of electrons it brought. How many electrons did the oxygen bring to the party?
It's up above there. Can you show me?
I don't think we wrote it down.
Oh, it's on the periodic table?
Yeah. Do you remember?
No.
Okay, let me bring up the periodic table here. Whoops.
Okay, it's in the 6th column, so it brought 6.
Very good. So we take how many electrons this oxygen brought, 6, and we subtract how many it has right around it.
Was that 7?
That's right. 1, 2, 3, 4, 5, 6, 7. 6 minus the 7, so we say that this oxygen right now has a -1 formal charge. What's the formal charge on that oxygen? You folks at home should try to find the formal charge on this oxygen before Fred does. Push pause if you need some time.
Let's see. It brought 6 minus 1, 2, 3, 4, 5. So that's a positive one.
Very good. It brought 6 minus 1, 2, 3, 4, 5, right? So that's a +1 formal charge. Whoops, +1. Now, do you know what it means to have positive or negative formal charges?
It means the molecule's not good, right?
That's right. So what can we do to fix the molecule?
We need to... I'm not sure.
We need to rearrange electron density, okay? We need to, instead of having, this has a +1, not enough electron density over here. This has a -1, too much electron density over here. We need to adjust these electrons so that there's less electron density over here. Again, that -1 charge, that -1 formal charge helps us know where there's too much. And we need more electron density over here. So I can do that by bringing a bond and making it into a lone pair electrons on that oxygen. So the result would be like that. Now, how has the formal charge changed here? What's the new formal charge? Folks at home, you should calculate the formal charge. You need to know how to calculate formal charges. So do that before Fred tells us. Okay, go ahead. Tell us, Fred.
The formal charge there is 0.
That's right. It brought 6 electrons. That's how we calculate the formal charge. How many it brought minus how many it has right around it. 1, 2, 3, 4, 5, 6. So that's 0. Good. So we've improved the formal charge. The formal charge over here is still the same, -1. But the problem is now carbon has a problem.
What's wrong with it?
Well, take a look. See if you can tell.
I can't tell.
How many electrons does it have available to it?
Oh, it only has 6.
Yeah, because we took some electrons away from that bond there. So now it needs more electron density. So this has a couple of problems. Its formal charge is, it brought 4, it has 3 right around it, has a +1, but it doesn't even have access to 8. So this wouldn't even be a feasible molecule right now because not everybody has a filled octet. However, I could bring electron density over here like that, and the result would be this structure. And we see that the formal charge on both of the oxygens is the same. It's 0. The carbon has access to 8 electrons, and its formal charge is also 0. Okay, so that then tells us that that is the most feasible structure for carbon dioxide. All right, two bonds on each side, one double bond on each side, 8 electrons available to carbon, 4 right around it, right? Okay, very good. Let's try the next one, HCN. HCN. Okay, what do you think is the central atom of HCN?
You said carbon always likes to form central atom.
Okay, very good. So what do I do now?
Draw hydrogen and nitrogen bound to it.
Very good. Hydrogen and nitrogen bound to it. Then what?
Count up the number of electrons.
Very good. Folks at home, count the number of electrons, push pause, and then push play. How many electrons did you get, Fred?
10.
That's right. 5 here, 6, and then 7, 8, 9, 10. So we have 10 valence electrons. What's next?
You have to subtract 4 because you already have 2 bonds.
All right, so our skeleton model had 4 valence electrons in it. So I have 6 valence electrons left to deal with. Where are you going to go first?
On the central atom.
All right, so folks at home, you should be a step ahead. So every time we say something, push pause, and then you do it. And if you get stuck, then push play and watch what happens. But you want to stay a step ahead. So if I put 4 valence electrons, that gives me an octet.
Yeah.
All right, so 4 valence electrons used up, 2 more valence electrons left.
You could put those on nitrogen.
All right. But now I'm out of electrons, and what?
We're in a world of hurt.
That's right. We have some problems, don't we?
Yep.
How can we fix them?
Well, maybe the folks at home know.
Do you guys know? Well, push pause and try to fix it and then see what happens. All right, Fred, here, I'm going to show you. If we take these electrons and bring them in here, right, make them bonds, carbon will still have them available to them, but then nitrogen will have more electron density available to them.
I know that.
Oh, okay, all right. You already knew. I should have asked you what to do. Okay, so then we'll have a triple bond like that, and we'll have a hydrogen like that, right? So carbon has now available to it 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen 1, 2, 3, 4, 5, 6, 7, 8. How about formal charges? Can everybody calculate the formal charges? Push pause and calculate those formal charges. Okay, Fred, what are they?
Nitrogen has a formal charge of 0 because it brought 5 electrons and now it has 5 right around it.
That's right. Carbon?
It's 0 also. Brought 4 right around it.
Very good. So that shows us that that is our structure for hydrogen cyanide. Okay? Excellent job.